Hello everyone, I'm Rahul Iyer from the University of California at Berkeley, sharing my research in modeling and control of the Flying Capacitor Multilevel converter. Power converters are everywhere in the modern world. We typically see passive components dominating converter volume and can make converters more compact by re-evaluating passive component utilization. Switching devices used in power electronics achieve higher performance when designed for lower blocking voltages, motivating designs with series-connected low-voltage devices. These trends have motivated research into flying capacitor multilevel converters. The FCML converter enables reductions in filter magnetics volume and use of low-voltage switches rated for a fraction of the input voltage. A key challenge in operating this converter is ensuring that capacitor voltages are balanced at their nominal values. During line transients, excessive voltages can appear across the switching devices. My work analyzes closed-loop active balancing control of the converter to ensure that the capacitor voltages remain balanced. I first developed an averaged model to relate the switch duty ratios to the converter state variables. I then show how the balancing controller can be implemented in parallel with standard average current control schemes. The design fully decouples the state variables, allowing independent balancing and output current and voltage regulation. Line transient characterization shows significantly improved balancing performance with the active balancing approach compared to natural balancing. However, active balancing controllers designed from average models exhibit small signal instabilities at light loads. To explain these instabilities, I developed a refined model of the converter using generalized averaging. Compared to the standard average model, generalized averaging captures both the impact of the inductor current ripple on the capacitor voltages and the dynamics of the current ripple. For typical designs, the feedback dynamics modeled by generalized averaging are significantly faster than the dynamics of the average state variables, and can thus be approximated through their DC gains. This yields a practically useful reduced-order model. I demonstrated through experimental verification that small signal analysis of the generalized average model accurately captures the instabilities of active balancing controllers derived from averaging. Finally, I studied new ways for modeling the capacitor voltage dynamics by studying the flow of charge, which offers simple expressions that are valid at light loads. The current in each subinterval is analyzed, the changes in flying capacitor charge are identified, and an average expression for the change in capacitor voltages is obtained. I then identified suitable perturbations to the switching signals and analyzed the corresponding changes in capacitor charge. I verified the resulting model against experimental verification of a hardware prototype. Using the new model, I then designed a state feedback controller to regulate the flying capacitor voltages. The proposed controller achieves significantly improved performance over the natural balancing dynamics and is stable at light loads. In summary, my work studies modeling and control techniques for reliable operation of FCML converters. Please be sure to reach out on LinkedIn or on email if you would like to ask me any questions or want to learn more. Thank you.